Hello everyone. In this video, we will explain basic principles of feedback control. We're going to talk about benefits of high-gain feedback, we're going to talk about disturbance rejection, and some other properties of a feedback control algorithm. Before I start, I'm going to give you a brief overview of what you're going to learn in this video. We're going to start with the simple mass spring damper system, and we're going to explain basic principles of feedback control approach in such a system. Why do we use mass spring damper systems? Well, mass spring damper systems can be used to represent or to model a large number of dynamical systems. Then we are going to derive a block diagram of such a system. And then finally we are going to derive, using Laplace transforms, expressions for displacement and the error for such a system. And on the basis of these expressions, we are going to make some useful conclusions about how a simple proportional controller is influencing the system performance, and we will see that basically high gain feedback can enable us to perfectly position such a system and to do disturbance rejection. In order to help you to better understand basic principles of feedback control, I have created a post that nicely summarizes everything that I will explain in this video. A link to this post can be found in the description below. Okay, so let us start. What you can see over here is a relatively simple model of a large number of dynamical systems. This is a mass spring damper system, so we are assuming that there is a mass or an object that's being attached to a damper and to a spring. And at the same time, you assume that there is a control force that's used to steer this mass or this object to a desired position. At the same time, we assume that there is a disturbance force acting on this system. What are the variables here? The variables, actually the main variable is the displacement. This displacement measures the position of the object from its equilibrium position. Our goal is to design a control algorithm and a control system that will steer this object to a desired position. For example, we want to steer this object from this position to this position over here. Now, the first step in designing a control method or control algorithm is to measure how far is our system from the desired position. For example, if this is the desired position, that in our case will be denoted by R, standing for a reference, and if this is the initial position or displacement denoted by x of t, the error or the control error measuring how far is our object from the desired position. For example, in this case, the error is r minus x of t, so this will be the error. So the control algorithm should react on the basis of the value of this error. The control algorithm should take as an input the value of error, and on the basis of this value of error, the control algorithm should be able to generate the control force F that will steer our object from some initial position to the desired position. Obviously, if error is high, this should imply that the control force should be high. Vice versa, if the error value is small, this should imply that the force should be small. Now I'm asking you the following question. What is the equation, a very simple equation that can represent this relationship? I give you 2 seconds to think about it. Well, the simple equation, or the simplest possible form of the control algorithm that exists, is the so-called proportional control or proportional controller. The proportional controller has the following form. The generated force is equal to some constant k, scalar constant in our case, times the error. So if error is high, the force will be high. If the error is small, the force will be small. If error is 0, the force will be equal to 0. So the main control problem is to determine this gain, the control gain, such that certain control objective is being achieved. Obviously, to achieve this type of control, we need to have feedback information in order to compute the error. That is, we need to have a real-time or more or less real-time information about the displacement of the mass or the displacement of the object. For that purpose, we need to install a sensor. And here I have symbolically represented a sensor by an eye. Looks like a human eye. Okay, this is a pupil. Now, this sensor provides information to the controller. So this block over here, marked by dashed lines, is the controller. Roughly speaking, the controller consists of 2 parts. The first part is a digital controller and supporting devices. So when I say supporting devices, I mean here data acquisition cards, signal conditioning circuits, and other circuits, right? So this is a digital controller, and this digital controller computes the value of control actions. Usually these are the voltages that are being sent to an actuator. An actuator, on the basis of these voltages that are sent to the actuator, to the amplifier of the actuators, and to mechanical parts of the actuators, such as, for example, rotational parts of a stepper motor, of a DC motor, or linear actuators. These actuators will generate control force or control torque that will move the mass, despite the influence of the disturbance force. In my previous post, I have explained how to model this system using transfer functions. I'm going to click on this link that will lead us to that post. So here's the post. You can read this post before watching this video, or you can stop at this moment and you can read this post and watch the video I made about this post in order to get yourself familiar with the basic system model. Okay, in interest of time, I'm just going to skip a few steps and I'm going to start from this equation. So this equation is the system model in the Laplace domain. X is the Laplace transform of the position or displacement. W1 is the transfer function from the force to the displacement, and W2 is the transfer function from the disturbance to the displacement. These transfer functions have this form that you can see over here, where A and B are constants, as well as tau1 and tau2. This system is stable, meaning that all the poles of this system are in the left half of the complex plane. This block diagram summarizes the working principle of a feedback control algorithm. This is the model of our plant. It's a mass spring damper system. We're assuming that there exists a sensor measuring the displacement, the position. Then, this feedback loop provides us information to compute the control error. The control error is equal to the difference between the reference signal and the actual position of our object. The reference position is the desired displacement of our mass. It's set by the user. It can be 5 meters, 10 meters, 0.1 centimeters, depending on the system and depending on your application. Now, the controller takes this error as an input and it computes the control force, right? However, at the same time, we are having a disturbance force acting on the system, so the joint effect of disturbance and control force creates a resultant force that's being actually applied to the plant. Our main task is to determine the parameters of this controller, that is, to determine the parameter k such that we can accurately position our object, that is, such that the actual position of the object in steady state matches the reference position. And at the same time, we want to minimize the effect that the disturbances are exerting on our system. To find the value of our controller gain, we need to do some math. As always, right? You should not be afraid of mathematics if you want to study control engineering. So let us write our basic equations. What do we have? We have that E of t is R of t minus x of t. Then we have that force of t should be equal to control gain times the error in time. And let us assume for simplicity that we want the reference signal to be constant and equal to some desired value, and that the disturbance acting on the system is constant, 4 times larger than equal than 0. Okay, so these are our basic equations. Now, what do we do next? Of course, we need to perform Laplace transform. So let us perform the Laplace transform of these equations. So let's see, the first equation is given here, right? And this equation corresponds to this equation. Similarly, the Laplace transform of the second equation is over here, and the Laplace transform of the third equation and the fourth equation are given over here. Just a small digression. Why Laplace transform of R of t is equal to 1 over s times Rd? Well, because Rd is constant, and we know that the Laplace transform of a constant is 1 over s times that constant. Let us now recall the basic equation representing the system dynamics. We have x of s is equal to w1 f of s plus w2 of s times d of s. Now, If we substitute first the second equation and then the first equation in this equation, we will obtain this equation. This term here is E of S, and the expression from here to here is nothing less than F of S. Now, if we massage this equation a little bit, that is, if we group F of X, actually X of S, if we move this variable on the left side, and if we group the expressions together, we will obtain consequently this equation, and if we divide everything by 1 plus W1 of S times K, we will obtain this final expression. So this expression is the so-called closed loop form of our control algorithm. It can tell us directly how R of S is influencing the displacement, taking into account the feedback connection. Now, if we substitute R of S and D of S in this equation, we will obtain the equation 8. And the equation 8 is nothing less than a step response of our feedback control system. The step response is computed as a superposition of the step response with respect to the control input and the step response with respect to the disturbance force. Next, let us assume that K is selected such that the poles of these two transfer functions are in the left half of the complex plane, that is, these transfer functions are stable. Since these transfer functions are stable, if we recall the final value theorem, the final value theorem will tell us that the steady state position in the time domain, or the limit value when t goes in infinity x of t, is equal to limit value when s goes to 0, s times the Laplace transform of the position. This is a fundamental theorem for analyzing the behavior of control systems. Now, let us compute these limit values. So, if we substitute the equation 8 in equation 10, and if we do a little bit of calculations, and if we recall the basic rules of computing limits of rational functions, we will obtain our final expression, that's fundamental expression in control systems. The fundamental expression is summarized by this equation. Here, to compute this equation, we need to evaluate these limit values, and just for a second, let us stop here and explain what is this over here. So, in order to compute the steady state in this equation, we need to compute the limit values of this term, and of the term over here. So let us see the first term, the term over here. What do we have here? Limit when s goes to 0 of this expression. Since this is basically a continuous function, we can evaluate this limit easily. It's just equal to ak. Similarly, the other expression, the expression in the denominator, becomes 1 plus ak, and the expression in the numerator of the second expression, it becomes equal to b. So if we substitute these three values in the equation 11, right, we arrive at the equation 13. And the equation 13 is the fundamental equation for analyzing the effect of the feedback control algorithm on the displacement. Besides this equation 13, there is another equation, that's equation 15, that basically tells us the steady state error as a function of the control gain k. This steady state error is obtained from the equation 13 using basically equation 14, right? And from here we can obtain the expression for the error. So let us analyze these two equations. So what do we see over here? Now, remember, the control goal is that XSS becomes RD. So let us see when this expression can be satisfied. Let's observe this equation over here. Now, obviously, if AK goes to infinity, the first term will become something like this. And this becomes equal to what? Equal to 1, approaches 1. Similarly, let's see what happens with the second term. And obviously, this becomes approximately over large. So the second term tends to 0. So what we have seen right now, we have seen the effect of the high gain feedback, right? Since this AK, this term here, is the gain of the feedback loop. By increasing K, we can increase the gain of the feedback loop, and consequently, what do we obtain? We obtain that XSS becomes approximately equal to 1 times RD plus 0 times D. So, if we increase K, if we increase the gain in a negative loop, our control objective will be approximately satisfied, even with a proportional controller, with a simple proportional controller. Let us confirm this by analyzing the error. Let's see what happens with the error. The first term, let's see what happens with the first term. Well, the first term is 1 over 1 plus AK. So, once AK is increased, this becomes 1 over 1 plus large value. And this becomes 1 over approximately, if AK is very, very large, and this becomes approximately 0, right? So the first term tends to 0. How about the second term? Well, we analyzed the second term. We concluded the second term also goes to 0. So ESS, when AK, the product of A and K is large, approximately tends to 0. So, what I have explained right now is the principle of the high feedback gain. This is a control principle for positioning the object and for computing the control gain. That is, if the value of the product A times K is high, then we achieve small steady state error. This means that our object will practically reach the desired destination, and the second thing we achieve is good disturbance rejection. However, you should be very careful here, because for certain classes of systems, as we will see in our future videos and in future posts, I will try to explain that high gain feedback can destabilize the control system. So do not blindly increase the feedback gain in the proportional controller. You always need to tune something else, right? So be very careful, and you will see in numerical example what happens if you boost the feedback gain. The system might become unstable. So there should be always some trade-off between the stability and how fast system reacts. We will explain this later. Now, another good side of the high gain feedback is that we increase the robustness of the system. So the system becomes more robust, and I will explain this in my future video. Now, another thing that we should analyze is what is the gain of the feedback control over the open loop control. So if you click on my previous post, the one I introduced at the beginning of this video, and the link is given over here, we can find, using similar analysis to the analysis I presented over here, we can find the steady state displacement and the steady state error of an open loop controller. And these two steady states are given by these two equations. Now, K again is the control parameter, however it is just an open loop controller. What we can see immediately over here, we cannot influence the disturbance. We cannot affect, with this controller, we cannot affect the disturbance. And the same thing can be seen by analyzing the steady state error. You cannot affect this part over here. On the other hand, let's see what happens in the case of the feedback control algorithm. So in the case of the feedback control algorithm, we can obviously see that we can affect two parts. We can have an effect of two parts by choosing a feedback control gain, K. We can affect the disturbances, so we can diminish this term, and by increasing K, we can make sure that this term here is equal to 1. So we will achieve approximately XXS is equal to RD. Okay, so I will stop here, and I have to say that in my future videos I'm going to present you MATLAB codes for verifying the performance of a feedback control algorithm, and in the subsequent videos I'm going to numerically demonstrate you, and using simulations, what are the positive and negative sides of high gain feedback. Thank you for your attention. I hope that you like this video. If you like this video, please subscribe. Have a nice day.